There is a moment, right before you fall asleep, when your thoughts stop making sense. Images that don't connect. Words without sentences. A kind of dissolving. You don't fight it. You just let it happen. And somewhere in that loosening, consciousness slips away. Most people don't think much about that moment, but it points to something that science has spent centuries trying to understand. Order is fragile. It takes effort to maintain. And without that effort, things don't hold together. Now scale that feeling up. Not to a person, not to a city, but to everything. Every star, every atom, every system in the known universe is subject to the same pressure. The tendency toward disorder. The slow, unstoppable drift toward randomness. Physics has a name for it. And once you understand what it actually means, the fact that you are sitting here right now, thinking, becomes one of the most improbable things in the history of the cosmos. The law is called entropy, and it is almost always misunderstood. Most people hear the word and think of destruction, of things falling apart, rusting, decaying, collapsing. And that's not wrong, but it's not the whole picture. Entropy isn't really about destruction. It's about probability. Systems move from less likely arrangements to more likely ones. A room stays messy because there are far more ways to be messy than to be clean. Smoke spreads through a room because there are far more ways for the molecules to scatter than to stay together. A glass shatters and doesn't reassemble because a broken glass is simply more probable than an intact one. The universe, in other words, isn't being pulled toward chaos. It's just drifting toward what's most likely. And what's most likely, almost always, is disorder. This is the second law of thermodynamics. It is one of the most robustly confirmed principles in all of science. No experiment has ever violated it. No system, anywhere, has ever been observed to spontaneously move from disorder to order without energy flowing in from somewhere else. The law holds. Always. Which makes what happened on this planet roughly 4 billion years ago almost incomprehensible. Life is, by any reasonable measure, the most organized thing we know of in the universe. A single human cell contains more functional complexity than any machine ever built. It reads information, copies it, repairs errors, converts energy, communicates with neighboring cells, and responds to its environment, all simultaneously, all within a space too small to see. Multiply that by 37 trillion, and you have a human body. An arrangement of matter so improbably structured that, measured against the backdrop of cosmic history, it should not exist. And yet, here we are. The question isn't just philosophical, it's scientific. How does a universe that trends toward disorder produce something like this? How does chaos make life? To find the answer, you have to go back, not just to the beginning of life on Earth, but to the conditions that made it possible. And what you find, when you look carefully, is that the question itself contains a false assumption. We assume that entropy and life are opposites, that one destroys and the other builds. But that's not quite right. The relationship between them is stranger and in some ways more beautiful than that. Life doesn't fight entropy, it uses it. Here's what that means. Entropy increases when energy spreads out, when it moves from a concentrated state to a dispersed one. The sun is an enormously concentrated source of energy. Space around it is cold and diffuse. Energy flows from the sun outward, spreading, dissipating, fulfilling the second law. And in the path of that flow, something interesting can happen. When energy moves through matter, it doesn't always do so smoothly. Sometimes it creates conditions where certain molecular arrangements become stable, not permanently, but long enough to matter. These arrangements aren't random. They are structures that happen to be good at capturing energy and passing it along. They persist because they are useful to the flow, not despite the flow. Think of a whirlpool in a river. The river is moving erupted constantly, releasing heat and chemical compounds from deep within the planet. Lightning discharged through an atmosphere rich in nitrogen, carbon, hydrogen, and oxygen, the basic ingredients of organic chemistry. The oceans were warm in places, superheated near hydrothermal vents on the seafloor, where mineral-rich water emerged from cracks in the crust at temperatures that would kill any modern organism. This was not a calm environment. It was a cauldron. And in that cauldron, chemistry was happening on a scale and at a speed that is difficult to imagine. Molecules formed and broke apart. Amino acids assembled from simpler compounds. Lipids, which have a natural tendency to organize themselves into membranes, began to form tiny enclosed spaces, primitive boundaries between inside and outside. And somewhere in all of this, something remarkable occurred. A molecule appeared that could copy itself. Not accurately, not intentionally, but enough. That moment, whenever and wherever it happened, changed everything. Because once you have a molecule that replicates, you have the conditions for evolution. Copies that are slightly better at surviving make more copies. Copies that are slightly worse disappear. Over time, through nothing but chemistry and probability, and the relentless pressure of natural selection, complexity accumulates. What begins as a self-copying molecule becomes a cell. What begins as a cell becomes, over billions of years, everything that has ever lived. This process is not separate from entropy. It is driven by it. Every organism alive today is a system that maintains its internal order by continuously drawing energy from the environment and releasing heat, increasing the disorder of everything around it. Your body right now is taking in organized chemical energy from food and releasing it as warmth, as carbon dioxide, as waste. You are, in thermodynamic terms, a machine for increasing the entropy of the universe. You maintain your own order by accelerating the disorder of everything else. Life doesn't defy the second law. It fulfills it, more thoroughly, more efficiently than almost anything else in nature. That, if correct, would be one of the most profound ideas in modern science. He suggests that life isn't just consistent with the laws of thermodynamics. It's predicted by them. That under the right conditions, matter will naturally organize itself into structures that dissipate energy more efficiently. That life, in this view, is not a cosmic accident. It is what physics looks like when you give it enough time and the right ingredients. This idea remains controversial. It hasn't been proven, but it hasn't been disproven either. And the fact that it's even plausible changes the question we should be asking. Not, how did life manage to arise against all odds? But, given the laws of physics, was life ever unlikely at all? And that question leads somewhere unexpected. If life is a natural response to energy flowing through matter, if it emerges wherever the conditions are right, then the universe may be far more alive than our silence-filled sky suggests. The same chemistry that sparked life on this planet exists across the cosmos. The same elements, the same reactions, The same physics. Hydrothermal vents have been found beneath the ice of Europa, one of Jupiter's moons. Complex organic molecules drift through interstellar space. The building blocks are everywhere. We don't know if life arose elsewhere. We haven't found it. But the silence of the sky, the absence of any confirmed signal from beyond, none of that proves absence. It may simply mean that life is quieter than we imagined, or rarer than the chemistry suggests, or that the universe is so vast that even common things are separated by distances that make contact nearly impossible. What we do know is this: for the first time in the history of this planet, possibly for the first time in the history of the universe, matter has organized itself to the point where it can ask why it exists. That is what you are. Not a mistake, not an anomaly, a temporary, improbable, extraordinarily complex arrangement of atoms that the universe assembled through billions of years of entropy and chemistry and evolution into something capable of looking back at the cosmos and wondering. The disorder is still coming. The stars will still burn out. The black holes will still evaporate. The heat death still waits, infinitely patient, at the end of time. But before that, here, now, in this small window of cosmic history, something organized itself out of the chaos. Something became aware. Something asked the question, and the fact that the universe allowed that, even once, may be the strangest thing about it.